Hello everyone, welcome, thanks for joining in, and thanks to the Cochrane Statistical Methods Group for the invitation to speak. I'm going to be presenting some work linking the areas of meta-analysis and joint modelling of longitudinal and time-to-event data. To give you an outline of what I'll be talking about today, I'm going to start by giving you an introduction to what exactly a joint model is. I'm then going to talk about aggregate level meta-analysis of joint data, talk about individual participant level meta-analysis of joint data with an illustrative example, and I'll talk about both two-stage and one-stage approaches, and then the presentation will end with a few conclusions and recommendations. So to start with, we're going to talk about exactly what a joint model is, and we're going to start that off by talking about the two main types of data that are key to a joint modelling analysis. So the first of these is longitudinal data. Longitudinal data is any data that's repeatedly measured over time. So individuals will provide multiple measurements over a time period. So for example, the study period. Examples of longitudinal data include weekly blood pressure measurements, biomarkers measured repeatedly in a study, results of tests performed regularly on patients in a hospital. The key point is that we have measurements measured repeatedly over time that are nested within individuals. Measurements from the same individual will of course be more similar than measurements recorded from different individuals, and we need to account for this nesting or clustering structure when modelling longitudinal data. Longitudinal data is commonly modelled using linear mixed effects models if the longitudinal outcome is continuous. If it's not continuous, their extension generalised linear mixed effects models is commonly used, although other approaches do also exist. Now, methods for both aggregate level and individual participant level meta-analysis of longitudinal data have been proposed in the literature. Aggregate or study level data longitudinal meta-analyses experience quite a few different problems due to studies reporting results at completely different time points and also not reporting correlation structures across different time points. Many aggregate data meta-analyses of longitudinal data actually perform separate meta-analyses at each time point. So for example, a meta-analysis at baseline, at 6 months, at 1 year. This is not advisable as it ignores correlation over time, and also the set of studies contributing to each meta-analysis at each time point will be completely different, depending on what time points they themselves reported in their studies. That's a form of publication bias, which is quite a big issue. Individual level participant data meta-analysis of longitudinal data requires a lot more statistical expertise, but it can actually be performed using the same methods as for a single study case. You just allow for an additional layer of nesting, so you now have measurements nested within individuals, nested within studies. And you can fit such models using standard statistical software, and such approaches allow proper modelling of correlation structures and also trends over time. The second important type of data for a joint analysis is time-to-event data, which records the time until some event occurs, for example, the time until death or the time until treatment withdrawal. The important thing to note is that not all individuals in the dataset will experience the event of interest. It's possible that some individuals will drop out for reasons unrelated to the event of interest, or some might reach the end of the study without ever experiencing the event. We term these individuals as censored. These individuals still contribute a lot of information to the study, the information that they've not experienced the event up until the time that they were censored. And it's important to account for this censoring process whenever modelling time-to-event data. Commonly, time-to-event data is modelled using approaches such as the proportional hazards model, accelerated failure time models, and also flexible parametric models. The literature dealing with meta-analysis of time-to-event data is extensive. As with longitudinal data, due to its complex nature, aggregate level meta-analysis of time-to-event data can be challenging. Parameters might be reported at different time points. Studies might not have used the most appropriate methods. They might have ignored censoring. Individual participant level meta-analysis of time to event data does require a lot more statistical expertise, but it's generally recommended to ensure that the complex data is correctly modelled. Existing, for example, proportional hazards models can be extended to account for the nesting, for example, by using mixed effects or by stratifying the baseline hazard by study. And again, there are some key references for meta-analysis of time to event data there at the bottom. So moving on to joint data, there are many examples in the literature where a particular disease area produces both longitudinal and time to event data. This type of data is referred to as joint longitudinal and time to event data, or more briefly as joint data. For example, a high hypertension dataset might include both regular blood pressure measurements and also time until a cardiovascular event. The reasons for employing models for joint longitudinal and time to event data can be grouped into three main categories. The first is when you have a longitudinal study where individuals drop out for reasons related to your longitudinal outcome. For example, if you are longitudinally modelling PANSS scores in schizophrenia data, often those with higher, as in worse PANSS scores, drop out over time, leaving a healthier and healthier population. If you don't account for this dropout, you will end up with biased, for example, treatment effects. Alternatively, you might be interested in a time to event study, but you have time varying covariates that you want to model. For example, the analysis of a biomarker on the risk of a disease progression. If you model this using an extended Cox model, for example, you assume that the value of the time varying covariate remains constant between measurement times, which again can give you biased results. The final category is when you have both longitudinal and time to event outcomes, which are both of equal interest. The hypertension example falls into this category. You might equally want to model blood pressure over time and also the time to cardiovascular event. Whichever category your research area falls into, whenever you have potentially related longitudinal and time to event data, it's very important to model them jointly. It not only allows you to investigate the relationship between the two, modeling them separately could lead to biased results. So you model joint data using a joint model, which was first produced in 1997 by Wolfson and Ciatis. But since then, the methodology has been expanded into a wide range of areas, including multivariate or multiple longitudinal, multiple time to event models, curate models, competing risks models, and also meta-analytic models. In their basic format, a joint model consists of three main components: a longitudinal submodel for the longitudinal outcome, a time to event submodel modeling the time to event outcome, and finally an association or linking structure, which quantifies the relationship between the two different submodels. Joint models simultaneously model the longitudinal and time to event outcome. This is different to previous methods that used a two-stage approach that first models the longitudinal outcome and then takes estimates from that longitudinal model and inserts them into a time to event model. By modelling simultaneously, again, you reduce the risk of biased results, so a joint model is preferred over a two-stage approach. The best way to think about a joint model is using this kind of picture. So we have a longitudinal submodel and a separate time to event submodel, and the link between these is represented through some association structure. More formally, using algebraic notation, this is what a joint model would look like for a single study analysis. So again, we have a longitudinal submodel and a time to event submodel linked through an association structure. The longitudinal response is generally modelled using a linear mixed effects model. Here we have the longitudinal outcome represented by Y, with I indexing an individual and J indexing a time point. The fixed or population effects are represented using beta terms, with the subscript identifying whether the beta term comes from the longitudinal submodel, subscript L, or from the time to event submodel, subscript S. Random effects, which can vary by individual, are represented by a lowercase b, and then finally the epsilon term in the longitudinal submodel is just an error term. In the time to event submodel, we represent the individual specific hazard using lambda I, and the population baseline hazard represented by lambda 0. Now, the joint model comes in through the association structure. So we express the linear predictor in the longitudinal submodel, the sum of the fixed and the random effects, as the W1 term. The association structure then takes this W1 term and takes some function of it to give the W2 term. This W2 term is then inserted into the time to event submodel, thus linking the two submodels. So there are a wide range of different association structures, each with different interpretations. I'm not going to go through the algebra of these. I'll just focus on how you actually interpret what they mean. The first that I'm going to talk about is the random proportional association structure. And I'm going to focus on this one because most of the analyses performed in this webinar use this association structure. The random proportional takes the difference between the population average and a given individual and quantifies how much that affects their risk of an event. So if you have an individual who has much higher blood pressure than the average population, does that mean that they're at a higher risk of an event? The other association structures listed here are also commonly used. The current value takes the value of the longitudinal marker at time t and quantifies the risk of the event based on that current value. The slope expresses how the rate of change of the longitudinal marker affects risk of an event. So does a sudden drop in your marker mean that you're at a much higher risk of an event? The weighted cumulative tells you how the history of your longitudinal marker affects the risk of an event. Interaction allows the relationship between the two submodels to differ across different groups, for example, across different treatment groups. And lagged means that you can allow the effect of the longitudinal outcome on risk of an event to be delayed by a certain amount. So now that we've seen what a joint model looks like, how commonly are they actually used in practice? So there was a review conducted in 2016 that aimed to assess the current use of joint models as applied to medical datasets. The papers included in this review had to apply methods to an existing dataset rather than develop any new joint modelling methodology. And the plot you can see on this graph shows the number of published joint modelling analysis by year from 1997, when the first joint model was introduced, up until 2015, which is the end of the search strategy. The red lines indicate key events in joint modelling literature, for example, the release of textbooks or seminal papers on the topic. As you can see, there's a clear trend over time of researchers starting to use joint modelling analysis, and this was across a range of disease areas, including cancer, HIV, transplant studies, and also modelling cognitive decline. As the number of joint data sets available in the literature increases, it becomes more and more important for us to be able to collate this information across studies in a meta-analysis. However, meta-analysis of joint data will inherit all of the issues of meta-analyses of longitudinal data, of time to event data, and it will also have its own inherent things to consider. So we're now going to talk about aggregate level meta-analysis of joint data. First off, is it actually feasible to perform a meta-analysis of joint data at an aggregate level? As we mentioned before, there are many issues with aggregate data meta-analysis of longitudinal or of time to event data. So it's likely there will also be issues when performing aggregate level meta-analyses of joint data. The review I mentioned before also assessed for the identified applied studies whether they actually reported sufficient information to contribute to theoretical future meta-analyses. To contribute sufficient information, they had to report effect estimates for each submodel and the association parameter, variance estimates, and also a sample size. I should point out that the review at that time did only contain 65 studies. However, of these, just under 70% reported sufficient information that they could contribute to a meta-analysis of effects in either the longitudinal submodel or in the time to event submodel. The reporting of the association parameter was a little better. About 76.9% of the studies were able to contribute to that one. But this is to be expected as quite a few of the studies would have been most interested in the relationship between the two outcomes, and so might have better reported the association parameter. However, we also tried to split results according to the reasons stated for using a joint model. So were they interested in accounting for dropout in the longitudinal component, or using time varying covariates in the time to event component? Not all studies reported a reason for using a joint model, and some reported many different reasons. However, if we examine the 22 studies that say that they used a joint model to account for dropout in the longitudinal component, you can see that the longitudinal component is much better reported than the time to event component. So we're not seeing full reporting of the results from a joint model, even in supplemental information, and the parts of the joint model that are reported are linked to the reason for using a joint model. So this might not be an issue if the purpose of the meta-analysis is similar to that of the original included studies. However, if the meta-analysis poses questions that extend the original purpose of the study, this poor reporting of aspects of the joint modelling analysis could hamper aggregate data meta-analyses in the future. So overall, there are potential issues with current reporting standards of joint models in the literature, which could make it hard to perform aggregate level meta-analyses of joint data. Additionally, there are a wide range of different specifications possible for both the longitudinal component, the time to event component, and the association structure when using a joint model. Often the structure of the joint model used was not well reported, meaning that in an aggregate level meta-analysis, it might be difficult to confirm exactly what model has been fitted and whether the parameters from the models are actually comparable, whether they should be pooled. As such, if you're planning a meta-analysis of joint data, you should be prepared that an IPD meta-analysis is probably the best way forward, as it avoids issues with reporting of results. You can standardize methods across studies, you can properly model effects over time, and care can be taken to make sure that the complex structure of the joint data is properly represented. So now we're going to move on to individual participant level meta-analysis of joint data. And I'm going to start by introducing an illustrative example dataset that I'll be using throughout the rest of the webinar. It's a subset of the INDANA dataset containing any study that provided both individual level longitudinal and time to event data. It's a dataset of hypertensive patients providing longitudinal continuous systolic blood pressure and time until death. And patients have been coded as either receiving treatment for hypertension or not receiving treatment for hypertension. I should highlight that initial plots of the longitudinal trajectories showed that the average trajectory showed an initial drop at about 6 months and then a bit of a plateau. So all of the example models I'm including include a function of time to account for this strangely shaped trajectory. I should also point out that this example is only illustrative. If this was a real analysis of hypertensive data, there are many other covariates that should be included in the model, for example, smoking status, age, but we've just presented a simple model to explain how to use a meta-analytic joint model. Before performing any type of IPD meta-analysis of joint data, there are a few preliminary steps that should always take place. Firstly, a range of summaries and graphs of the data should be produced to get an initial feel for the data and to assess potential modelling approaches, to look for potential indicators of a relationship between the longitudinal and time to event outcomes. These preliminaries are a good idea regardless of whether you're performing a one-stage or a two-stage individual participant data meta-analysis. The time to event plots that you would produce are similar in nature to the ones that you would produce for a separate time to event analysis, so I'm not going to focus on them here, but I will focus on the types of plots that you should produce for the longitudinal component because they differ to separate longitudinal analysis plots that you might produce. And I'm going to point out some of the interesting features of them. So the first plot that you should produce, and you should produce these plots for each study in your meta-analysis separately. The first plot plots the longitudinal outcome y against the longitudinal measurement time t, and the plot is panelled by event type, so whether the individuals in question were censored or whether they experienced the event. The trajectories of all individuals in the dataset can be, in the study-specific dataset can be plotted, but if the sample size is too large, do just plot a sample or a subset of the available individuals, otherwise the structure of the data will be hard to see. This example is for the COOP study from the Indana dataset. We've also put a smoother over the data so that we can see the average longitudinal trajectory for the study, and this trajectory is the one that we're trying to model using the fixed effects in our joint model. Interestingly, we can see that the data is quite noisy, but we can see this initial drop in the first couple of months in the data, followed by a bit of a plateau. If you look at the event, the people who've experienced the event, it almost looks like their blood pressure is dropping over time, whereas the blood pressure for the average blood pressure trajectory for those censored is staying relatively high. And that is at odds with the disease area. We wouldn't really expect the blood pressure for those not experiencing death to stay high. The reason for this is that we have longitudinal data that's related to our time to event data. We can see this best if we go and look at a second type of plot. This second type of plot still plots the longitudinal outcome, but it plots against time adjusted by survival time. So for each individual, we've taken their survival time away from their longitudinal measurement times. This means that we're plotting their trajectory as they're moving towards their event or censoring time. So as we move towards 0 on the x-axis, we can see what happens just before they're censored or just before they experience the event. So we can now see that the mean longitudinal trajectory for those censored drops just before they leave the study, before they're censored, whereas those that experience the event, those that die, remain at a higher level of blood pressure. So we wouldn't have seen this unless we'd produced this plot panelled by event type and adjusted by survival time. So because we've got a difference in the mean trajectory between those censored and those events, we have evidence that we should be using a joint model rather than separate analyses. There's a relationship between the longitudinal and the time to event components. So we will now move on to actual analysis of longitudinal data. And we will start to talk about two-stage IPD meta-analysis of joint data. The general process of a two-stage joint data meta-analysis is the same as for most two-stage IPD meta-analyses. We take the data from each study separately, we fit a joint model to the data from just that study. We identify and extract any parameters of interest. In these examples, we're just interested in treatment effect and the association parameter. We also extract any measures of variability that we need, and then we pool the extracted measures just using standard meta-analytic techniques. Graphically, this can be shown like this. So we start with study-specific datasets. In stage 1, we fit separate models to each of these datasets, and in stage 2, we take the estimates from each of these models and pool them. So for a joint model, the first stage of a two-stage IPD meta-analysis would look like this. We again have a longitudinal submodel that contains a fixed intercept, time, treatment, and function of time term. These fixed terms have subscript k, representing that we're going to get fixed effects estimates for them from each study. We also include in the longitudinal component individual specific random intercept and random slope. So we allow each individual to differ in their longitudinal intercept and also in their longitudinal trend over time. As before, the W1 term is the linear predictor of the longitudinal submodel. The time to event submodel contains just a fixed treatment effect, which again is estimated for each study, as is the baseline hazard. The final term in the time to event submodel is the W2 term, which is the association structure. In this example, we're using a random proportional association structure. So we're taking the individual specific random effects from the longitudinal submodel and inserting them with common coefficient into the time to event submodel. and the terms highlighted in orange are the ones that we're going to extract and perform meta-analyses for. So we're extracting the treatment effect from both submodels and the association structure. In the second stage, we would just pool the extracted parameters of interest and their variances using standard meta-analytic techniques. We've performed here a separate meta-analysis for each parameter of interest using an inverse variance approach. As in all meta-analyses that use an inverse variance approach, the weighting in the meta-analysis is the inverse of the effect variance for fixed effects meta-analysis and the inverse of the sum of effect variance and between study heterogeneity for the random effect meta-analysis approach. So applied to our example dataset, here are some of the results. This is for the longitudinal treatment effect coefficient. So being assigned to a treatment for hypertension versus not being assigned to a treatment for hypertension unsurprisingly reduces blood pressure significantly in each study. However, the effect of treatment is highly variable across the different studies. We should note that over half of the individuals in this dataset belong to the MRC1 study, and the MRC1 study actually includes patients who are about 20 years younger than any of the other studies. So we know this is a heterogeneous population, so it's not surprising that the treatment effect estimates are quite different. If we move on to the treatment effect estimate from the time to event submodel, we see that we don't really have an effect of assignment to treatment on risk of death. We don't have a direct effect of it. Again, results across studies are variable, and we've got a very different result from the STOP trial than the other trials. But if we look at the meta-analysis of the association parameter, we start to see something quite interesting. The association parameter quantifies the link between the submodels. In this case, the interpretation is that a positive association parameter is interpreted that individuals with above average systolic blood pressure scores are at higher risk of experiencing the event, death. Again, we have variable results from studies. MRC1 again provides a different result to most of the other studies. The pooled results are positive but not significant for the random effects meta-analysis. From talking to clinicians, it's suspected that different types of treatments might have different effects, and also that different subgroups of patients might have different relationships between the longitudinal and time to event components. So we're planning on conducting further joint analyses that use the interaction association structure instead, and also that analyze this in a network meta-analytic format. Interestingly, there's possible evidence here that although treatment did not directly affect risk of death, treatment did directly affect systolic blood pressure, which is related to risk of death. So we might have an indirect effect of treatment through the association structure, which we wouldn't actually pick up if we performed separate longitudinal or time to event analyses. There are many considerations with two-stage individual participant data meta-analyses of joint data. And these considerations link in a way to the aggregate data meta-analyses that we talked about before, especially this first example. So what happens if different types of association structures are used across the studies included in your meta-analysis? Consider if you had one study that employed a current value association structure. So you've shared the entire longitudinal trajectory, apart from the error term, into the time to event submodel. And then consider a second study that shares only the random effect. So that second study has used a random proportional association structure. The interpretation of the association parameters is very different. Alpha C in the first study states the effect on risk of an event given the value of the longitudinal component at time t. Alpha 2 in the second study only represents the risk of an event given the individual deviation from the population mean. So if we pool these two association parameters, alpha C and alpha 2, we're assuming that the effect on risk of an event of the fixed component of the longitudinal model is 0, which is quite a strong assumption. A second example along the same line is more relevant to two-stage meta-analysis. Suppose that you have the same type of association structure across studies, so both of these studies are using the random proportional association structure. However, due to the model specification, the terms shared in the association structure differ. So our first study employed an individual level random intercept and random time term in the longitudinal component. The second study only included an individual level random intercept. Both used a random proportional association structure, but the terms linking the two submodels are again different. Again, if you pool these two association parameters, you are assuming that the effect of individual specific slopes on risk of an event is negligible. So care should be taken to only pool parameters whose interpretation is comparable, because otherwise your assumptions about what has an effect on risk of an event can be quite strong. A few recommendations for two-stage IPD meta-analysis of joint models. As with any joint IPD meta-analyses, first the data from each study should be plotted. This will help to identify potential random effect structures, shapes of trajectories, and also whether there actually is a relationship between the longitudinal and the time to event components. This graphing procedure should help you identify appropriate modelling structures for each study. And when you fit a joint model to each study, you should be very clear about the specification of each study, the specification of the model for each study. If the specifications of the joint models are identical across studies, parameters should have the same interpretation and so can be pooled. If model specifications differ across studies, then care should be taken to consider exactly what the interpretation of each parameter in each study is, especially the association parameters. Only parameters with comparable interpretations should be pooled. To show this in picture format, if you had 7 studies in a two-stage IPD meta-analysis, you would examine the data in each study and consider the most appropriate joint modelling structure to fit to the data from each study. Here the studies fall into 2 main groups. You would fit model specification 1 to the studies in group 1 and model specification 2 to the studies in group 2. You would then meta-analyse results from group 1 and separately meta-analyse results from group 2. If the same modelling structure is not considered appropriate across all studies, this should motivate consideration of whether the studies themselves are comparable or whether the studies from different groups differ in some characteristic that could explain this difference in modelling structure. So, for example, was one group showing individual specific trends over time and another group was not, and why was this happening? Now we're going to leave two-stage approaches and move on to one-stage IPD meta-analyses of joint data. So again, we're going to start with an overview of the process for one-stage IPD meta-analysis of joint data. This process again will be similar to the process for most one-stage IPD meta-analyses. As before, we start by producing the preliminary plots and summaries of the joint data. They should be performed to assess the link between the longitudinal outcomes, to assess the modelling structure for the longitudinal trajectories, for example, the random effect structure, and to highlight again, when we did this for the Indana, we noticed that there was a change point in the trajectory. If we hadn't plotted the data, we might not have noticed that. Once these preliminaries have been completed, the first step is to construct a large metadata set that holds the data from all studies in a single large data set, with a study indicator noting which study the data originated from. After that, a single joint model is fitted to this multi-study dataset, and it's vital to ensure that the clustering of data within studies is represented in the model. In a joint model, there are a wide range of different methods to represent clustering, through study-level random effects, fixed interaction terms between study membership and other covariates, which could be included in either of the longitudinal or time-to-event submodels, by stratification of the baseline hazard in the time-to-event submodel, or through some combination of these approaches. It's vital, as I will show you later, not to ignore clustering in the data, as it could severely affect the estimation of certain parameters. Again, a representation of this process is shown here. So holds the data from all the studies 1 through K in a single large metadata set, and in the first and only stage of the meta-analysis, we fit a single joint model to all the data in the metadata set at once. I'm now going to go through 3 examples of possible one-stage meta-analytic joint models fitted to the illustrative hypertension dataset from earlier. In all three examples, we have a joint model that uses a random proportional association structure. So the longitudinal and time to event submodels are linked through shared random effects only. In this first example, clustering of data within studies is accounted for just using study level random effects. Throughout these one-stage examples, any term that's highlighted in orange is a term that helps to account for clustering of our data within studies. So here we can see that we have an a study level random intercept and random treatment effect in the longitudinal submodel, which are present in the time to event submodel through the association structure. The longitudinal submodel again contains a fixed intercept, time, treatment and function of time term, as well as the individual level and study level random effects. The association structure shares the random effects between the submodels. The random effects at each level are split. So we have a separate association parameter for the individual level and for the study level. This allows us to see the difference in risk of an event due to the individual level random effect and the study level random effect. The time to event submodel, we just have an unspecified baseline hazard lambda 0, a fixed or population level treatment effect, and then our association structure. So we're managing to account for clustering in our data in each submodel and also the association structure through the shared random effects. However, there are a range of benefits and drawbacks of accounting for clustering of data within studies using study level random effects in a joint model. Benefits are that you estimate a distribution for the differences between studies, which allow you both to assess how variable the currently included studies are, but you can also predict future studies. Additionally, as the number of studies included in the meta-analysis increases, the number of parameters stays constant given the number of random effects included in your submodel, which means that your model doesn't become cumbersome quickly, which is especially important in the joint model because we have the multiple different submodels. Drawbacks include that to estimate a distribution for the random effects, especially because they're so important in a joint model, they're used in the association structure as well as the submodels. You need to have sufficient studies included in your meta-analysis to estimate them reliably. If the number of studies included is small, the distribution of study level random effects could be poorly estimated, which could then have a knock-on effect on estimations of other parameters. Additionally, some softwares might not automatically output study-specific values for the random effects, only the values for the actual distribution. The second example employs just fixed study membership terms and their interaction between study membership and treatment. We can see that we've had to include these fixed terms separately in each submodel, so we've got them present in the longitudinal submodel and the time to event submodel. However, because they're fixed effects and because we're using a random proportional association structure, this approach ignores any between study heterogeneity present in the association structure. So it again has a couple of issues. Benefits include that you automatically obtain exact study-specific estimates for example, treatment effect from your joint model fit, and you completely separate out study-specific effects between your longitudinal submodel and your time to event submodel. If you think back to the study level random effect approach, the between study heterogeneity in each submodel has to kind of be proportional to each other. By using fixed effects, we're not limiting it to be proportional. Finally, this approach may produce more reliable results than study level random effects when the number of included studies in the meta-analysis is small. Drawbacks of this approach, though, include that the approach very quickly becomes cumbersome as the number of studies included in the meta-analysis increases. For each new study that we include in this meta-analysis, we would need to include 2 new parameters in each submodel, so 4 new parameters per new included study. So the model would very quickly become unwieldy. Additionally, we have limited ability to predict results for future studies as we don't generate a distribution of study effects. And finally, there's no way, as I mentioned, of accounting for heterogeneity in the association structure using this approach. The third and final example uses a mix of different approaches. So clustering of data within studies is accounted for in 3 different ways. We've got a fixed study membership term in the longitudinal submodel. the baseline hazard in the time to event submodel is stratified by study, and then we've got a random study level treatment effect that's present in both submodels through the association structure. So a little bit of everything. Again, benefits and limitations. Benefits are that this model is actually incredibly fast to fit, and it's because we're separating the baseline hazard by study. So all of these models that I've presented here use an unspecified baseline hazard. So the vector of event times is much shorter if we're just using study-specific baseline hazards. However, there are quite a few drawbacks with this mixed approach. We've got the issue that as the number of studies increase, the approach becomes cumbersome because we're adding parameters for each study. When we stratify the baseline hazard by study, we do explain, but we do account for, but we don't explain heterogeneity between studies. We've got the issue that our study level random effects might not be well estimated unless we have a big enough number of studies, but that could make the fixed effects cumbersome. And finally, because we're accounting for heterogeneity in 3 different ways, it can become quite complex to interpret the approach. We've got part of the heterogeneity represented by a distribution, part of it by a fixed effect. It can become quite difficult to interpret. So we'll now look at the results of those 3 examples, as well as a naive approach that ignores clustering. Applied to the illustrative hypertension example. So again, we're going to look at the longitudinal treatment effect, the time to event treatment effect, and then finally the association parameter. As with the 2-stage approach, from the 1-stage approach, we can see that all of the studies estimate a significant negative treatment effect. So being assigned to a treatment for hypertension significantly reduces your blood pressure, again, unsurprising. But there's an obvious issue with a model that just accounts for clustering using study level random effects. The magnitude of this treatment effect estimate is much lower than any of the other approaches, possibly due to the fact that we're trying to estimate a multivariate normal distribution using just 6 studies. And I should also highlight that the estimates from the STOP study using the fixed approach are again very different to the estimates from the other studies. Then we have the results for the treatment effect for the time to event submodel. Again, for the same set of modelling approaches. Again, the results are very similar to those from the 2-stage meta-analysis. The treatment effect is again insignificant in every case apart from the STOP trial for the fixed effect approach. So again, we don't have much evidence that assignment to treatment for hypertension directly affects the risk of an event. But the really interesting thing happens when we look at the association parameters. Now, every modelling approach that we performed included an individual level association parameter, alpha 2. So that's present in all of our approaches. Only approaches that involved a study level random effect have reported alpha 3, which is the association parameter linked to the study level random effects. The individual level association parameters are always positive and significant, indicating that in our meta-analysis, a higher longitudinal outcome, so a higher systolic blood pressure, an individual with a greater than population average systolic blood pressure is at higher risk of having an event. So we've seen from the longitudinal treatment effect that we have a significant treatment effect, that treatment reduces blood pressure. We've also seen that we have a significant relationship between the 2 outcomes. So we have evidence that we have an indirect effect of treatment via blood pressure through the association structure, which we would not have seen in a separate longitudinal or a separate time to event analysis. We should highlight that the naive approach at the top of the table that ignores clustering produces a very different association parameter than the approaches that do account for clustering. The association parameter is much larger in magnitude. So by ignoring clustering, we're getting very biased results. So it highlights, especially for the association parameter, we should not go anywhere near ignoring clustering. Finally, the results for the approaches that use study level random effects, the approach that just uses study level random effects, we've got a very different estimate for the alpha 3 association than for the mixed approach at the bottom. Also, in the paper that this analysis is taken from, it presents a couple of other models. Again, the study level random effect approach is very, very different to the other approaches, which again gives us more evidence that we don't have enough studies in this case to just account for study level heterogeneity using random effects. So, overall recommendations. We'd recommend that, as with a two-stage IPD meta-analysis, the same preliminary summaries of the data and graphs are produced to allow assessment of the shape of the longitudinal trajectory, assess potential random effect structures, and also look for initial evidence of a relationship between the longitudinal and time to event components. Care should be taken to account for clustering in a one-stage model, as a naive model that ignores clustering is likely to produce biased results, especially for the association parameter. However, due to the structure of a joint model, with parameters shared across submodels, care must be taken not to account for the same between study heterogeneity twice. So imagine you included a study level treatment effect in your longitudinal component, and a fixed treatment effect interacted with study membership in your time to event component. Through the association structure, you'd have two parameters actually modeling the same thing. Consider the association structure you're using and be clear which parameters it means that you're sharing between submodels, and make sure that when you're fitting the joint model, you understand the interpretation of all the parameters and where exactly they appear. Finally, consider the number of studies that you've included in your meta-analysis. Random effects are especially important in joint models, as they're not only used to account for heterogeneity between studies or individuals, they're also used to link the submodels. Consider whether you have sufficient studies included in your meta-analysis to adequately model their distribution. A quick note about software. Joint models nowadays can be fitted in many different packages, including SAS, Stata, Winbugs, and many more. However, all the analyses presented in this webinar have been done using R. Key packages to be aware of are single study joint modeling packages that could be used in two-stage meta-analyses, which are Joiner and JM. Multi-study joint modeling packages, which are Joiner Meta and Joiner Meta Bayes, which is still in progress. And then meta-analytic packages to be used in the second stage of two-stage meta-analyses, Meta and Meta-4. So, a summary of recommendations. Overall, joint models are growing in popularity as a method of simultaneous modelling of potentially related longitudinal and time-to-event data. So there's a growing resource of joint datasets. Meta-analysis of joint data is possible, but individual participant data is probably required. Two-stage approaches are simple to implement using existing single-study joint modelling approaches and software, but they are limited in their ability to investigate heterogeneity between studies. One-stage approaches are more complex and must be adequately specified to account for clustering, but do give greater scope to investigate heterogeneity. Generally, one and two-stage approaches should give similar results under most circumstances, but differences could arise due to differences in model specification between approaches. There's a great paper in the references that talks more about that if you're interested. So I'll leave you with some key references on all of the areas I've talked about. And I'll just finish by thanking the many contributors to this work, including my sponsors, Professor Catherine Tudor-Smith and Dr. Ranthi Kolamanaj-Donna at the Department of Biostatistics, University of Liverpool, and also Dr. Francois Gaffier from the University of Lyon, who is my clinical sponsor.